So let's consider how to create an ROC chart and what it means. So here's our data set. This time we are seeing the data set sorted by probability. Okay, so it's the same data set, it's just that we have rearranged the rows so that the high probabilities are on top and the low probabilities are on the bottom, and it's decreasing. Okay, so now what we are going to do is we are going to consider many alternatives for the cutoff probability. And for every alternative, we want to look at the trade-off that occurs between the true positive rate and the false positive rate. Okay, so let's do this. Let's take a look at considering each of these probability values as the cutoff. Okay, so what we want to do is first consider the probability, the cutoff as infinity. Okay, that's outside of this. So with an infinity cutoff, which means in order for something to be considered as as a true, as a positive case, the probability has to be infinite. So obviously, nothing will be considered as a positive. Okay, then we'll consider the highest probability as the cutoff, and for every such value, we will calculate the false positive rate and the true positive rate. Now, what do we mean by false positive rate? Okay, now by false positive rate, what we mean is the number of false positives divided by the total number of false cases, which are in this total number of negative cases in the system, right? Because you can get a false positive only when you take something which is negative and classify it as a positive. Okay, so let's take a concrete example. I think that'll make it better for us. Okay, so if you take the cutoff as 0.903, right, then what will happen is that you will identify this row as a positive, right? You'll classify this as a 1 because if the cutoff is 0.903, this is the one with 0.903 probability. So this will be classified as a 1. Everything else will be classified as a 0. Okay, so if your cutoff probability is 0.903, then your true positive rate is 0.2. Okay, that is, why is it 0.2? Because there are 5 positives, right? There are 5 positives in the data set and 5 negatives, and this will classify one of those 5 as positive. Okay, and therefore the true positive rate is 0.2, 1 out of 5. Okay, and the false positive rate is going to be 0 because nothing is going to be falsely classified as positive, right? Because everything else is going to be classified as negative, as 0. This one alone is going to be classified as 1, right? So nothing which is a 0 will be classified mistakenly as a 1. So the false positive rate is 0, the true positive rate is 0.2. Okay. Next, if we consider the cutoff as 0.831, then these two will be classified as 1. Everything else will get classified as 0 because all the others have a probability, have a probability of less than 0.831, and the cutoff is 0.831, which means these two will be classified as 1. Everything will be classified as 0. So therefore, your false positive rate is still 0. Okay, true positive has now become 0.4 because 2 out of the 5 we have found. Okay, so both of these are classified as positive, and they are both true positives. They are both actually also positive. Okay, so we go on like this. If you do 0.6, that is, if you do a cutoff of 0.703, once again, all of these 3 will be classified as 1, and they are indeed 1. Therefore, your true positive rate is 0.6, 3 out of 5. Still, we have not done any false positives because all the remaining guys are going to be classified as zeros, right? So none of the actual zeros will be classified as 1. So the false positive rate still remains as 0. Okay. Now, if we go down here up to the next, using a cutoff of 0.596, right, then our true positive becomes 0.8 because we will classify all of these 4 as 1s, and they are all indeed 1s. Okay, so the true positive rate becomes 0.8 and the false positive rate is still 0. Okay, so now we start getting some false positives. If we use a cutoff of 0.558, okay, then what that means is we'll classify all of these first five, anything which has got a probability of 0.558 and above, we'll classify that as 1. Okay, of course, you still get a true positive of only 0.8 because that'll mean that these four which we classified as 1 are correctly 1. They are actually 1, right? So that is 4 out of 5 which is true positives. So that's 0.8. But we now have classified this 0 also as a 1 because we said cutoff is 0.558. So this 0 gets classified as a 1. So we now get a false positive rate of 0.2, right? Because there are 5 potentially false positive cases because we have 5 zeros. Out of those, one of them we have actually classified. So we've got a false positive rate of 0.2, true positive rate of 0.8. Okay. Now if you use a cutoff of 0.508, our true positive still remains 0.8, corresponding to these 4 ones. But false positive now goes up to 0.4 because 2 of these will be classified as positive, but that would be incorrect. Okay, again, we do a cutoff of 0.378, same thing. This is still a false positive. Okay, now if you do a cutoff of 0.02, then you capture the last true positive. So now at this point, if your cutoff is 0.02, then you will classify all of the things with a probability of about 0.02 as 1, 0.02 or more as 1. And that'll mean that all of these 4 plus this will all get classified as 1, and they will all be true positives, and there are only 5 positives in the data set. So your true positive rate now becomes 1.0. You found all the true positives that you can find, and the false positive rate at this point, of course, still remains as 0.6, right? Because these 3 zeros that you would have incorrectly classified as 1. So your true false positive rate is 0.6. Okay. Now, of course, the true positive cannot go any further beyond 1. So it will remain as 1, and the false positive will slowly climb to 0.8 and then to 1. Okay. So the final point, of course, is always going to be 1, 1.0, 1.0. So you can see here how when you decrease the cutoff probability starting from the maximum, right? You increase the true positive rate, but you will also increase the false positive rate until both of them become 1 when you consider all the cases. Okay, so what we want to do is to identify a point where the true positive rate is pretty high, but the false positive is not so high. Okay, let's try and see how this translates into an ROC curve, right? So if you plot an ROC curve, this is what it's going to look like. Okay, that's what an ROC curve is. On the x-axis is your false positive rate. On the y-axis is the true positive rate. And what we are going to plot is all of these points, right? So the first point is at 0, 0. That is when your cutoff is infinity. Okay, then of course there is no true positive, there is no false positive because there is no positive. So it's all 0. Then you come to this 0, 0.0, 0, 0.2. So that will be the point here. 0.0 false positive, 0.2 true positive. So that point will be there. Okay, so that's the first row. Then if you look at this 0.4, false positive 0, true positive 0.4, that is that point. Okay, then the next is that point, the next is that point, right? So here we have reached 0.0 and 0.8, 0.0, 0.8, right? So at this point, we are doing really well. We've got 4 true positives and no false positives. Okay, so if you use a cutoff of 0.596, then you will have a true positive rate of 0.8 and a false positive rate of 0, which is really good. That means what is happening is we are identifying only the true positives as only the actual positives as positives, and we are not falsely identifying any negatives as positives. Or if you want to talk in terms of Bayer's, and if Bayer is your positive class, what we are saying is 4 out of the 5 Bayer's we have already identified without having classified any non-buyers as buyers. Okay. Now the next 3 points as we go forward, we are not gaining any true positive, but we are gaining, three false positives here. Okay, those are 3 false positives that we have gained here corresponding to these 3, right? Then when we consider this row, we've got our final true positive. True positive rate has become 1. We have identified all the true positives that exist, and the remaining 2 points do this. Okay, so that's what is an ROC chart. Okay, so when you look at the ROC chart, you're interested in, and of course this line basically represents the 45-degree line. Okay, when the true positive rate and that is basically what you're saying is that this is the basic rate of the true positive and false positive that's going. Okay, this is the base rate that you have in the system. So for example, if you have if you go through this process and you're identifying true positives at the same rate as you're identifying the false positives, then you'll get this curve. That means your model is not helping you at all. Okay, the model is just predicting the natural proportions which exist in your data. That's it. Okay, but the point where we would like our cutoff probability would be essentially the point that is furthest away from this line, right? So this is the point which is furthest away from the line, and this point we already know represents a cutoff of 0.596 where we get this. Okay, so in some sense a cutoff of 0.596 is a really good value because it allows us to capture most of the true positives, 0.8. So 80% of the true positives you have already captured here without incurring the cost of any false positives as of this point. Okay, now when you keep on looking at lowering the cutoff a little bit further, you start now only capturing false positives. Okay, none of those is really useful. Okay, so now the cost that you're incurring to get this final true positive is the cost of these 3 false positives. Okay, so you want to see from a business point of view, does it make sense? Does getting that one customer, true customer, does it merit or does it warrant us to incur the cost of finding these 3 non-customers, treating them as customers and incurring the concomitant costs? Okay, so that's the idea of the ROC chart, right? So what you can do is you have your prediction model, right? And the model has calculated the probabilities. Then what you will ideally do is to plot the ROC chart, and I'll show you how to do that. You plot the ROC chart, and once you plot the ROC chart, it will give you a visual indication of what is a good cutoff point, right? So you can actually look and see which is the point where I'm capturing most of my true positives without incurring the cost of too many false positives. Okay, and then you go and find the cutoff corresponding to that and use that as the cutoff. We'll see that again, how to do that. Okay, so the trade-off between true positive and false positive is what your ROC curve is indicating. Okay, here are some example ROC curves. Okay, so you've got 5 ROC curves that are shown here. This of course is a diagonal, false positive, true positive, just like before. So the curve A looks like this, right? Your true positive is climbing all the way up to 1 with the false positive remaining at 0, right? What this means is that, as you keep decreasing the cutoff, okay, you're able to reach a point where you identify all the true positives, 100% of them, because it's gone all the way up to 1. You identify 100% of the true positives without incurring the cost of even one false positive. Okay, so that's completely ideal when your model is exact. Okay, when your model is absolutely exact, at least insofar as your test partition goes. So that of course is not going to happen in the real world. Okay, but that's the ideal. Okay, real world ROC charts would look more like B or C. Okay, so here what is happening is that initially you see a rapid rise of the true positive rate, right? That means the very high probabilities are quite good at identifying true positives, right? For example, if you have a probability of 0.9, 0.8, 0.7, all of those are true positives, or let's say buyers, right? So there's no mistake. There's no non-buyer for whom the probability, the model is saying the probability is 0.8 and 0.7. That's not happening. But you may have a non-buyer for whom the model is saying the probability is 0.55 or something like that, right? So that is why initially you get quite a few of the true positives. Then, in order to get true positives are still rising at a good rate, but you're incurring some false positives, right? When the curve goes to the right, that means false positive rate is increasing, right? So at the cost of increasing the false positive a little bit, you're still able to find quite a few true positives, okay? And you can see if after this point, you can see that the curve is starting to taper off, which means in order to get additional true positives, you have to get more of false positive, right? So the equation is shifting here, that the rate at which you see more false positives is higher than the rate at which you see new true positives, okay? So one might say that the point on the curve which is furthest from the line, okay, the vertical line if you draw, is probably somewhere here, right? That point is the one which is furthest away from the line, or I don't know if it's this point, okay? So you'll choose that point and take the probability that corresponds to that point, right? How do you find the probability corresponding to that point? You look at the false positive, true positive combination, right? And then you can go back to your data here and find that combination and take the corresponding cutoff. Okay, that's what goes on here. Okay, now B is a very good ROC chart, right? Because there's a very steep rise in true positive rate, and then the tapering off begins quite late. C is also a good ROC chart, right? So you do see a fairly rapid rise, but it's not as good as B, right? Because in order to get additional true positives, you're going to have to look at more false positives. So once again, if you look at the distance from the line, probably this is the point at which the returns start becoming not that great. Okay, D of course is a line where the model is not helping at all. E is absolutely terrible, right? E is the exact reverse of A. A is an accurate model. E is the exact opposite. Every positive is classified as a negative, and every negative is classified as a positive, right? So E is the complete worst classification model, ROC chart. Okay.